So we're looking at linear functions. We've talked about the form of a linear function, slope-intercept form. If the slope was positive, we know the line is increasing. If the slope is negative, it's decreasing. If it's equal to 0, we have a horizontal line. So now going into more detail on linear functions, suppose that you're having f of x is equal to 3x plus 5. And g of x is equal to negative 2x plus 15. So you should be able to do the following problems and be familiar with the notation that you're seeing. And so here we have f of x is equal to 0. So we're looking at our f of x function, 3x plus 5, setting it equal to 0 and solving. And so in here we know that we can get x by itself by subtracting 5 on both sides. So we would have 3x is equal to negative 5, and then dividing through by 3. So we get x is equal to negative 5/3. So solve f of x, which is less than 0. Well, as long as when we were solving our equation, we didn't divide or multiply by a negative number, then the inequality sign is going to stay the same. If we divided by a negative, then we have to flip the inequality. So I noticed when I solved for x here, I just subtracted 5 and I divided by a positive. So that would have kept the inequality the same when I had set 3x plus 5 less than 0. So we would get then that x is less than negative 5/3. So we want to know when is f of x equal to g of x. So we're setting both of the equations equal to each other and solving for x. So we have f of x here is 3x plus 5. And we're setting it equal to our g of x value. And our g of x value is negative 2x plus 15. So solving a linear equation, we want all the variables to one side, all the coefficients, terms without variables, to the other side. So I could add 2x to both sides, getting rid of the negative 2x on the right. So adding 2x to both sides, 3x plus 2x is 5x. And then subtracting 5 on both sides. So 15 minus 5, that would give us 10. And then dividing through by 5, we get x is equal to 2. We want to know when is f of x greater than or equal to g of x. So same idea, if hadn't divided or multiplied by a negative sign in part C, then we should get, our inequality will not flip. And so here we had x is greater than 2. Well, we added 2x, we subtracted 5, and we divided by 5. We did not divide by a negative. So f of x is greater than or equal to g of x when x is greater than or equal to 2. Next part says graph f of x is g of x and label the points that represent the solution to the equation f of x equals g of x. Okay. So our equations are already in the form y equals mx plus b. I noticed that my y-intercept for my f of x function is 5. So I'm going to plot that. So I have a point at 0, 5. I see my slope is 1. So if I go up 1, my slope is 3. So if I rise 3 and go over 1, so 1, 2, 3 over 1. So 1, 2, 3 over 1. So if I go down 3, I would go over 1 to the left. So down 3 from 5. We saw that our x-intercept was negative 5/3, so that's negative 1.6 about, and that's something's off of that, if that's right. Okay, so again, I have plotted that last point wrong, so that should have been at -1, 2, but our x-intercept we saw was about -1.7. Okay, so I'm graphing this line. We get something that looks like this. And this is our f of x function. Okay, so now let's look at plotting g of x. So g of x is also in slope-intercept form. We have a y-intercept of 15, and we have a slope of -2. So y-intercept at 15 and a slope-intercept at -2. So if I fall 2, go over 1 to the right. Fall 2, over 1 to the right. So graphing this. And we saw that the y, do we solve that one for x? No, we didn't. Almost there. So graphing it, we get a line. G of x looks like this. So it wanted to label the point where it represents the solution of the two equations. So we have found the x value where f of x is equal to g of x. That was when x was 2. And we can see here when x equals 2, this is where they cross. So to find the y value of that point, we can look at it. It looks like 14, or it looks like 11. But let's go back in and plug in 2 into one of those equations, and we should get back that value of 11 in either case. So if I look at f of 2, I go in and I plug into wherever I see an x and f of x, we would get that this is equal to 3 all times x, which is 2 plus 5. And 3 times 2 is 6. 6 plus 5 gives us 11. So our solution, when f of x is equal to g of x, is at the point 211. Let's just talk about it a little bit. Part D, where we are looking at f of x is bigger than or equal to g of x. So we're looking at when is the y value of f of x bigger than the y value of g of x. And we saw that it was when x was greater than or equal to 2. So if we go up here, when x is greater than or equal to 2. So everything on the right of x equals 2, notice that that green line for my graph of f of x is higher than that purplish magenta line that is below as we get x is bigger than or equal to 2. So looking at the next problem is a word problem. So getting towed. The cost C in dollars to tow a car is modeled by a function C of x equals 2.5x plus 85, where x is the number of miles towed. What is the cost of towing a car 40 miles? Well, if we're looking at the cost of getting towed 40 miles, We know that x is equal to the number of miles. We're going to go into our function, c of x, and we're going to plug in 40 wherever we see an x. So we have 2.5. I see an x here. I'm going to replace it with a parentheses plus 85. And then I'm going to drop in my 40 into wherever I saw an x. So 2.5 times 40. Well, I know 2 times 40 is 80. And half of 40 is 20. So that should be 100. Plus 85 is equal to 185. So the cost of 40 miles is going to be $185. So if the cost of the towing a car is $245, how many miles was towed? So we know what C of X is. We know that the cost is $245. So we have 245 is equal to, and we're trying to figure out what X is in this case. So 245 is equal to 2.5X plus 85. We're trying to solve for X, so we want to get X by itself. Let's subtract 85 on both sides of our equation. So 245 minus 85, let me just make sure I did that right. 5 minus 5, 6, is 160 is equal to 2.5 X. And then let's divide both sides by 2.5 to get X by itself. So X here is equal to 64. So the cost of $245 to tow the car was towed 64 miles. Suppose that you have only $150. What is the maximum number of miles that can be towed? So we only have $150. And so we know that C, we want our C of X, our cost, not to be more than this $150. So we want that cost to be less than or equal to 150. Okay, so looking at this, we have our cost function, which is 2.5x plus 85 is equal to 150. Oops. Let's subtract 85 on both sides. So I have 2.5x is equal to 65. Divide 65 by 2.5, and we get 26. So we can be towed a maximum of 26 miles. And then part D, what is the domain of C? So when we're looking at the domain, we need to kind of think about our word problem, if it's a word problem. We're talking about getting towed. We're talking about X being the number of miles being towed. So it doesn't make sense to be towed a negative number of miles. And so I know that X should be greater than or equal to 0. if I was looking at the domain of how much money I have and how much I could spend and the number of miles being towed, that would be then between 0 and 26 miles. So that would be the domain with constraints on the amount of money that we have to spend on getting towed. We're now jumping into a supply and demand problem. And so let's go through some of the terminology for this problem. So the quantity supplied of a good is the amount of the product that a company is willing to make available for sale at a given price. If we're looking at the quantity demanded, of a good is the amount of a product that a consumer are willing to purchase at a given price P. So let's suppose that the quantity supplies is S and the quantity demanded is D. Then the equilibrium price of the product is defined as the price at which the quantity is equal to the demand. Quantity supplied is equal to the quantity demanded. That is, the equilibrium price is the price at which quantity supplied equals quantity demanded, S of P equals D of P. So here's an example of a function below where we have a supply and a demand function. So the price is actually the independent variable, and the quantity supplied and quantity demanded, this is the dependent variable. It's on our y-axis. So if we're looking at S of P, let's just talk about what this line is saying. So looking at it, it looks like when we have a price where it's touching the x-axis, or in this case, the p-axis, we have a point at 60, 0. So when the price is 60, the supply that is given by the company is 0. But notice as our price increases, so does the number that the company supplies of that product. So they want more money, so they're going to supply more if they get more money for things. If we look at the other line, so right here where we're crossing the SD line, so our demand function at a price. So if it was cost $0, the demand here would be $2,850. But notice as the price increases, the demand of that product is going down. So now let's look at a word problem dealing with supply and demand. So the example says, suppose that the quantity supplied S and the quantity demanded D of hot dogs at a baseball game are given by the following function. So the supply is negative 2,000 plus 3,000 P. And the demand for the quantity is 10,000 minus 1,000 P, where P is the price of hot dogs. Find the equilibrium price for the hot dog at the baseball game. What is the equilibrium quantity? Okay, so equilibrium price is when our supply is equal to demand. And so we're going to look at when is SOP equal to DFP. So SOP is negative 2,000 plus 3,000 P. When is this equal to 10,000 minus 1,000 P? So we want to get P's to one side, numbers that don't have P on the other side. So if I add 1,000 P to my 3,000 P, that is going to give me 4,000 P is equal to adding 2,000 to both sides. So I have 10,000 plus 2,000 is 12,000. And then let's divide both sides by 4,000. And so we get P is equal to 3. So supply is going to equal demand when the price of the hot dog is $3. We want to find out what is the equilibrium quantity. So we can plug that into either one of those equations. And so if I plugged it into the demand, so D of $3 is equal to 10,000 minus 1,000 times P, but P we're plugging in 3. So this is equal to 10,000 minus 3,000, which is 7,000. So the demand of the number of hot dogs when it is selling for $3 at the baseball game is 7,000 hot dogs. That is the equilibrium price and quantity. So that was part A. Part B says determine the price for which the quantity demanded is less than the quantity supplied. So we wanted the demand, G of P, to be less than the quantity demanded, supplied. I'm putting SOP on the left-hand side just because I had done that with my equation here. So I want the supply to be greater than yeah. I want the what is demanded to be less than what was supplied. So notice I'm just looking to see if I had divided by a negative when I had done this, and I hadn't. So in here, I would have had that P had to be greater than or equal to 3. So the quantity demanded is going to be less than what is supplied if the price is greater than $3. So what do you think will eventually happen if the price of the dogs, if the quantity demanded is less than the quantity supplied? Well, if the price of the hot dogs is less, if the price of the hot dog if the quantity is demanded less than the quantity supplied. Well, if the quantity demanded is less than what they have supplied, then my guess is they're going to want to sell what they have on hand, and so they're going to probably decrease their price so that the demand will go up.